This is AS Chemistry, Chapter 2, Lesson 1 on ionic bonding. So let's start by looking at what ionic bonding is. And a lot of this is stuff that you may have seen at GCSE, or you certainly should have seen at GCSE. So ionic bonding occurs when a metal and a non-metal react together. So for ionic bonding, we always need a metal and we also need a non-metal present as well. And what ionic bonding involves is the transfer of electrons between atoms to form ions. So atoms will transfer electrons and ions will be produced. In ionic bonding, atoms will gain or lose electrons to form ions with a stable noble gas electron configuration. So the atoms will lose or gain electrons, and therefore one atom will get, if it loses electrons, it will develop a positive charge and become an ion. And the other atom, which loses or gains electrons, in this case, let's say gains the electrons, will develop a negative charge and become an ion. So one atom will lose electrons and gain a positive charge and become an ion. And one atom will gain the electrons and become an ion with a negative charge. So ionic bonding occurs when a metal and non-metal react together. There will be a transfer of electrons between the two atoms. Ions will be produced. One ion will have a positive charge and the other ion will have a negative charge. And we'll look at these in a bit more detail when we look at the dot and cross diagrams. The reason the atoms want to lose or gain electrons is to get a stable noble gas electron configuration. And again, we'll look at this when we draw the ions out. So we'll start by looking at sodium chloride. Sodium chloride, as the name suggests, is made from two elements. And the two elements that sodium chloride is made from is sodium and chlorine. Sodium is a metal and chlorine is a non-metal. And as we've seen on the slide before, a metal and a non-metal gives us ionic bonding. So in the case of sodium chloride, there will be a transfer of electrons between the sodium and the chlorine atom to produce an ionically bonded compound called sodium chloride. And to show this, we can draw a dot and cross diagram. So if we start off by showing the structure of a sodium atom and the structure of a chlorine atom, we can work out the dot and cross diagram quite easily. I'd always recommend that in an exam you only draw the outer electrons, because the inner electrons are not involved in bonding at all. It's only the outer electrons, the electrons in the outer shell, which are involved in bonding. So therefore it's a lot easier just to draw the outer shell electrons. It's also easier to use the model that you should have looked at GCSE, which is the 2882 model of writing the electron arrangement. So in the case of sodium, it's easy to say that sodium has 11 protons, therefore 11 electrons, and therefore the electron arrangement is 281, and therefore it's got one electron in the outer shell. Or you could simply say sodium is in group 1 of the periodic table, and the group number equals the number of electrons in the outer shell. So since sodium's in group 1, it has one electron in the outer shell. So you could draw on a piece of paper a sodium atom with one electron in the outer shell. Then draw a chlorine atom, and chlorine is in group 7, and it's got 7 electrons in its outer shell because the group number equals the number of outer electrons. So draw 7 electrons in the outer shell of a chlorine atom. What you'll be able to see easily from the picture is that in order for chlorine to get a full outer shell, it needs one more electron. And in order for sodium to get a complete outer shell, it needs to lose one electron. If we look at the A-level electron arrangement, then sodium's electron arrangement is 1s2, 2s2, 2p6, 3s1. And we can clearly see on this slide, I've coloured in red the outer shell, which is 3s1. In order for sodium to get a complete electron arrangement or a noble gas electron configuration, it needs to lose that 3s1 outer electron, and therefore its electron arrangement will become 1s2, 2s2, 2p6. In the case of chlorine, we've got 1s2, 2s2, 2p6, 3s2, 3p5. And in this case, we know that the p sublevel can hold a maximum of 6 electrons. So in this case, chlorine needs to gain one to get to 3p6. But that's a lot more difficult to write each time and to try and visualize what's happening. So it's easier to use the model from GCSE of the 2882 model, and it's easier to work out what's happening. And at the end of the day, what they're interested in is you being able to draw a dot and cross diagram and also be able to explain what's happened when the ionic bonding has taken place in that particular compound, what's happened in terms of gain or loss of electrons. So in terms of sodium, sodium being in group 1 has 1 outer electron, and chlorine being group 7 has 7 outer electrons. Chlorine needs 1 more electron if we look at these diagrams to become stable, and therefore sodium also needs to lose 1 electron to become stable. It can get a complete outer shell. So sodium loses 1 electron and chlorine accepts this electron, and therefore what we get to is a diagram where we have 2 ions. In this case, the sodium has now become an ion because it's lost 1 electron, and therefore it develops a charge which is plus. The chlorine has gained 1 electron, so it becomes an ion known as the chloride ion, and it develops a negative charge, and the positive and negative will attract to each other. Note I've drawn the electrons on sodium as dots and the electrons on chlorine as crosses. But there's no rule saying that you have to draw them as dots or crosses. You can draw them all as dots if you want, but it's just easier to see what's happening and visualize it when you've drawn it on a piece of paper. So let's do the transfer of electron from sodium to chlorine. And there it is. So the electron has been transferred from sodium to chlorine. Sodium has now lost the outer electron and it's got a positive charge. Note that ions are always written in square brackets. So I've now put the sodium atom, which I had at the start. I've taken the outer shell electron, removed the outer shell electron from the sodium atom. It's become an ion, so now I've drawn the inner shell and I've drawn square brackets and a positive charge on the outside. So this is my sodium ion now. Now note when you do draw your sodium ion from your sodium atom, don't just leave it with a complete outer shell which has got no electrons in it. So don't just leave one circle and say now the electron's been transferred. Always draw the inner shell. So if you remove the outer shell completely, always draw the inner shell. It's always very, very important. So don't just leave one circle on the outside, square brackets and a positive charge to indicate that the electron's been lost. They'll X you in the exam. Make sure that if you do show the outer shell being completely lost of an electron, then make sure you show the next inner shell which is complete. Okay, just like I've done here. You don't need to draw the inner shell electrons, which is the 2 electrons by the sodium atom's nucleus. Okay, so sodium ion's nucleus, you don't need to do that. In terms of chlorine, that picks up this electron. And once that's gained the electron, that will go from 7 to 8 in its outer shell. So there it is. It's gone from 7 to 8 in its outer shell, and it's developed a negative charge. So square brackets and a negative charge. The positive and the negative charge will attract to each other because they're oppositely charged, and that is the ionic bond that's taking place in sodium chloride. So that's the dot and cross diagram for sodium chloride. And in the exam, they will always ask you to draw the final structure, which is what you've got on this slide here. And again, you don't need to draw all the inner shell electrons, just the outermost shell will do. So 1 electron is transferred in this process. The metal will always lose the electrons or the electron, and the non-metal will gain the electrons or the electron. So sodium chloride is Na plus and Cr minus, and therefore the formula, since the plus and the minus cancel out, is NaCl for sodium chloride. Okay, let's look at magnesium oxide. You might wish to, at this point on a piece of paper, to draw out magnesium oxide and go through the same sequence that we went through for sodium chloride. So start by identifying the elements, then draw out the 2 atoms, then work out how many electrons are being transferred, and then work out the 2 ions that are produced in this particular compound. And you might wish to pause at this point, but I'm going to run through it now. So magnesium oxide is composed of magnesium and oxygen. They're the 2 elements. What we start by doing is drawing a magnesium atom and an oxygen atom. And again, it's easier to just use the GCSE model. So magnesium has 2 electrons in its outer shell. It's got an electron arrangement 282. Oxygen is in group 6 of the periodic table, and it's got 6 electrons in its outer shell. What we can clearly see from this diagram is that magnesium needs to lose 2 outer electrons. That's a 3s2 if we look at the A-level model. So it needs to lose 2 outer electrons, or in terms of the GCSE model, 282, it needs to lose those 2 electrons to get a complete electron arrangement of a noble gas. And oxygen, on the other hand, needs to gain 2 electrons to get to 8 in its outer shell. It's only got 6 at the moment. The GCSE rule is that it can have a maximum of 8 in its outer shell. So oxygen needs 2 more to get a complete outer shell to get 8 electrons, and magnesium needs to lose 2 electrons to have a full outer shell with 8 electrons. So there's an electron transfer where magnesium atom will lose 2 electrons, the oxygen atom will gain those 2 electrons, and we will produce 2 ions. The magnesium, having lost 2 electrons, gets a full noble gas electron configuration, produces an ion with a 2+ charge. The oxygen gains those 2 electrons and again gets an electron arrangement of a noble gas, but this time gets a 2- charge because it's gained 2 electrons. So there we go, we've shown our magnesium having lost the outer shell electrons. We must show it's now got a complete electron arrangement of a noble gas, so we must show a complete electron shell, which I've done in my diagram here. Square brackets indicating it's an ion and a 2+ charge on the outside. Oxygen's accepted those 2 electrons, or it's gained those 2 electrons, and therefore we've got a full outer shell again, square brackets and a 2- charge. 2 electrons have been transferred in this process. So magnesium oxide is Mg2+ and O2-, so the formula becomes MgO. Okay, there's lots of dot and cross diagrams you could do, and sometimes they're very, very similar to each other, and it's the application that's very, very important. So for instance, with sodium chloride, I could have written down potassium chloride, because potassium will still have 1 electron in its outer shell. I could have changed sodium chloride to sodium fluoride, sodium bromide, sodium iodide. The electron diagram, dot and cross diagram, would be still exactly the same. Remember, we're only showing the outer shell electrons, so the diagram would be exactly the same. The halogen in this case, whether it's fluorine, chlorine, bromine or iodine, will still have 7 electrons in the outer shell. And again, I could change the metal. Instead of sodium, I could go for anything in group 1. I could have changed that to potassium or lithium. Okay, and the electron diagram would be very similar. Note, for lithium, it would be slightly different because lithium only has 3 electrons in its outer, well, it has 3 electrons, so the electron arrangement is 2-1, and therefore once it loses the outer electron, you're left with an inner shell, well, you're left with an outer shell of only 2 electrons, and it might be easier to draw that on a piece of paper. So remember, they could ask you anything in the exam. Again, just draw out the atoms and then work out how many electrons are transferred and then draw the ions. That's the principle that you're trying to take away from certainly this lesson. So again, instead of magnesium oxide, we could take sodium oxide. And sodium oxide is slightly different. And try to draw it on a piece of paper. And then have a go at doing magnesium chloride. Now, sodium oxide and magnesium chloride are both different examples. So the first one we looked at with sodium chloride, there was a 1 electron transfer. Magnesium oxide, there was a 2 electron transfer. With sodium oxide, there's a completely different thing that's taking place, and with magnesium chloride. So if you start by drawing on a piece of paper a sodium atom, and you start by drawing an oxygen atom, what you'll notice is the oxygen atom has 6 electrons in its outer shell, and the sodium atom has 1 electron in its outer shell. Now it makes sense that sodium can lose that 1 outer electron to get a full electron arrangement of a noble gas configuration, just like we've seen. And oxygen, on the other hand, needs to gain 2 electrons, but sodium can only give 1 electron, and that's where the problem happens. And in this case, what we do is we double up the number of sodium atoms. So we draw 2 sodium atoms for 1 oxygen atom. And each sodium atom loses 1 electron. So each sodium atom loses 1 electron and gives it to oxygen. And oxygen will gain 2 electrons in turn. And therefore, each sodium atom, you'll have 2 of these in total, will get a positive charge. Make sure you show the full electron shell of sodium after having lost its outer electron. So each sodium ion will get a positive charge, so you'll have two sodium ions, each with a positive charge, a single positive charge, and the sodium ion now, which has now got 8 electrons in its outer shell, having gained 1 each from the sodium, will get a 2 minus charge. So you'll have two Na plus ions and an O2 minus ion, and therefore the formula of sodium oxide is Na2O. In the case with magnesium chloride, it's again slightly different, but if you've managed to do sodium oxide, you certainly should be able to do magnesium chloride. If you start by drawing a magnesium atom, that's got an electron arrangement again, which is 2h2, or you could just say it's in group 2, so it has 2 outer electrons. So magnesium's got 2 outer electrons. You've got chlorine, which has got 7 outer electrons. It's fairly clear to see that chlorine needs to gain 1 electron. Okay, so we can see that chlorine will need to gain 1 electron. But magnesium, on the other hand, needs to lose the 2 outer electrons to get a complete electron arrangement of a noble gas. So in order for it to get a stable noble gas configuration, it needs to lose the 2 outer electrons so it has a full outer shell of electrons. And in order for it to do this, chlorine can only pick up 1 electron. So we've got to solve this somehow. And what we do in this case is we double up the number of chlorines. So one chlorine atom will accept 1 electron from the magnesium atom, and then we bring in a second chlorine to accept the second electron from the magnesium. And what you'll notice is that magnesium loses 2 electrons, and therefore it's Mg2+, and each chlorine accepts 1 electron from magnesium, and therefore becomes a chloride ion with a negative charge. So you end up with a magnesium 2+ ion, and you end up with 2 negatively charged chloride ions. And again, the formula of magnesium chloride is MgCl2, which implies you've got Mg2+ and you've got 2 chloride ions. But the more you practice drawing dot and cross diagrams, the better you will get. Okay, moving on to a bit more about ionic compounds, moving away from these dot and cross diagrams, because dot and cross diagrams rarely come up in the exam. What does come up is the ability to recognize that it's actually the compound they've given you has ionic bonding, and the explanation of why ionic compounds have a very high melting point and why they don't conduct electricity when a solid, and how do we make them conduct electricity. That's the question that comes up very, very frequently, and that's what I'm going to focus on more. That's something I would encourage you to definitely make notes on. So ionically bonded compounds form a certain structure. So they form a structure. So if you've got a compound which contains ionic bonding, they will form a structure. And the picture of this, or a diagram of this structure, is shown at the bottom. And the name of the structure formed by a compound that has ionic bonding is an giant ionic lattice. Okay, you need the word giant ionic lattice. So that's the name of the structure. So in ionic compounds, the positive and negative ions are strongly attracted to each other. And that's because they are oppositely charged. Whether it's the Na plus ion and the Cl minus ion in sodium chloride, and that's what this structure shows you at the bottom, or it's the Mg2+ ion and the O2 minus in magnesium oxide. Because the ions are oppositely charged, one's positive and one's negative, they will strongly attract to each other. And what we say is that there is a strong electrostatic force of attraction between oppositely charged ions. And that's the crucial sentence which will get you 1 to 2 marks in the exam, depending on how lenient they want to be. But it's usually worth 2 marks. So there's a strong electrostatic force of attraction between oppositely charged ions. And this force is known as the ionic bond. And this 3D structure is known as a giant ionic lattice. Okay, so remember, it's called a giant ionic lattice. So if you've got ionic bonding present, the type of structure you form is a giant ionic lattice. And in a giant ionic lattice, there is a strong electrostatic force of attraction between oppositely charged ions. That's what's holding this big 3D structure together. So if you were to take a piece of salt, which is sodium chloride, and you were to zoom in with a very, very powerful microscope, just imagine you could do this. What you could see, you can't do this in reality, you would see a structure that looks like this, a giant ionic lattice. If you then zoomed in further onto the positive and negative ions, you'd see that dot and cross diagram that we've drawn for sodium chloride. Okay, so let's talk about the sodium chloride lattice in a bit more detail, Well, let's talk about any ionic lattice in a bit more detail. If you were to look at the sodium chloride lattice first, what we would notice, and this is just some useful things to remember, you'd notice if you look carefully that each sodium ion in the sodium chloride lattice is surrounded by 6 chloride ions, and each chloride ion in the sodium chloride lattice is surrounded by 6 sodium ions. And to show this, we could look at one of these diagrams here. This is quite a complicated diagram of an ionic lattice, and if you carefully count or look at the positive ion in the center, you'll notice it's surrounded by, say, 6 negatively charged chloride ions, and that's something you can see. But that's just something useful to know, that each positive ion in this case is surrounded by 6 negatively charged chloride ions, and each negatively charged chloride ion in this case is surrounded by 6 positively charged sodium ions. But it's not a requirement of the exam, just to show you how they are arranged. What is required for the exam is the ability to draw an ionic lattice, a giant ionic lattice. And unfortunately, you're not going to get away if you draw a lovely diagram like I've got on the left hand side. What you have to draw is this diagram that I've done on the right hand side, while you show a series of circles being linked together in a cube. Now what's easier to do is to draw the cube first. So draw a cube and then replace each kind of corner with a circle. So draw a cube and replace each of the corners with a circle. And keep doing this until you get that diagram on the right hand side, and keep practicing. And some will be better than others. So you start by drawing a cube and then you replace each corner by circles. In an ionic lattice, what we say is there's alternating positive and negative ions. And that means that no positive ion will always be next to each other. It'll be positive, negative, and so on. So sometimes you're expected to complete this diagram. Other times you're expected to draw the diagram from scratch. I draw a cube, replace the corners with circles, and then put the positive and negative ions in. I've started off by putting a positive ion in the corner. The next ion will always be a negative ion, and again positive goes to negative. The positive again will go down to a negative. So the positive ion will always be surrounded by a negative ion. Each negative ion will be surrounded by a positive ion. So if we continue, the negative ions will then go towards a positive ion. Again, negative ion will go towards a positive ion. Okay, moving on from there, the positive ion will be surrounded by a negative ion, and the negative ions will be surrounded by a positive ion. So if you look at the diagram very, very carefully, you'll see that each positive ion is surrounded by negative ions, and each positive ion, in this case, is nowhere near another positive ion. It's not directly next to one. It's not. Okay, and that's very, very important. So remember, we're looking at opposite charges in this diagram, and make sure you can do that. So what I recommend that you do is to draw a cube on a piece of paper. Once you've drawn a cube, replace the corners with circles. Start by putting a positive or a negative charge in any of the corner, and then make sure that every single time you move to the next circle, it's an opposite charge to the one that you drew, until you get a diagram that looks like this. And that's known as a giant ionic lattice. And you do need to learn the picture on the right for the exam. So let's look at their properties, and we've mentioned some of these properties before. The most important property that you'll come across is that ionic compounds have very high melting points. And what they'll often ask you in the exam is, why is this the case? Now what I've written is ionic compounds have very high melting points, as many strong ionic bonds need to be broken, which requires a lot of heat energy. That's fair enough. That is the reason why they have a high melting point. But that will only secure you 1 mark. What they want you to write in the exam, if they give you any ionic compound, sodium chloride, could give you anything, calcium fluoride, could give you any ionic compound that they can think of. Okay, so anything, rubidium chloride, I could pick anything with a metal and a non-metal. What they want you to state is that the type of bonding present, and note what I say. Start by writing that this compound has ionic bonding and forms a giant ionic lattice structure. Okay, we've highlighted the bonding and we've highlighted the structure in that one sentence. Then write that there is a strong electrostatic force of attraction between oppositely charged ions. That's absolutely crucial. The word there we're looking for is this attraction that is present between the oppositely charged ions. So there is a strong electrostatic force of attraction between oppositely charged ions. And then you need to say that many strong ionic bonds need to be broken, which requires a lot of heat energy. Or you could say a lot of energy needs to be put in to break this strong force of attraction, and therefore ionic compounds have very high melting points. So I'll say it once more. Start by writing that the compound is ionic bonding and has a giant ionic lattice structure. Then say that there's a strong electrostatic force of attraction between oppositely charged ions. And then go on to say a lot of heat energy is required to break this strong force of attraction. Therefore, ionic compounds have very high melting points. Ionic compounds in the solid state also don't conduct electricity. Now, the requirement for an ionic compound to conduct electricity is that the ions must be free to move. So the ions must be free to move. Well, we know in the solid state, so ionic compounds are always in the solid state when they're formed. In the solid state, the ions are packed together. If we were to talk about the ionic lattice, or the giant ionic lattice, we would say that the ions are in a fixed position and therefore cannot move. So therefore, in the solid state, ionic compounds cannot conduct electricity because the ions are fixed and cannot move. So in order to conduct electricity, the ions must be able to move freely. Now, there is a number of things that we can do to this ionic compound to make it conduct electricity. One of the things we can do is we can dissolve it. So we can dissolve it in water. Take a beaker, take our ionic compound, could be salt, sodium chloride, take a spoon of it, dissolve it into water, mix it around, and this ionic lattice breaks down. Or you could take sodium chloride, you could put it in some kind of dish and heat it up very, very strongly and turn it into a molten state. And when it's turned into a molten state, when it's melted, the ions are free to move. So to make the ions free and to allow them to move, what we can do is either dissolve it in water or we can turn it into a molten state by melting it. That's the two things that we can do with an ionic compound. So when molten, the lattice breaks up and the ions are free to move, and the ions can then carry a current, which allows it to conduct electricity. And when dissolved in water, the ions are free to move, and again they can carry a current. Now, quite often we can do something called a conductivity test, which is just taking a bulb with two metal plates coming from it, and the bulb is connected to a power pack. And this is something you might have seen. And what you can do is just put the two metal plates which are not touching each other. When they touch each other, then the current can flow from the main supply and can light up the bulb. But we're not interested in that. We're trying to use the solution to see if it's got any abilities to conduct. And what you can do in this case is put it into the solid ionic compound and the bulb doesn't light up. You might have seen this experiment. And you can take the two metal strips and put them into a solution containing an ionic compound which is dissolved. So sodium chloride has been dissolved in water. Put the two metal strips into there. Make sure the bulb is connected to the power supply. The two metal plates don't touch each other. Otherwise, it makes no difference if the solution conducts or not, because the two metal plates are touching each other. As long as they're not touching each other, dip it into the solution containing the ionic compound, and the ions will be able to conduct the electricity. And what you'll notice is that the bulb lights up. But that's just an experiment you might have seen before. And here it is again. So solid ionic compound does not conduct electricity because the ions are not free to move. But if you melt it or you dissolve it in water, the ions are free to move and it will conduct electricity. Okay, moving on to something a bit more challenging, something that I'd expect you to be able to do. In this table at the bottom, you've got two ionic compounds, sodium chloride and magnesium oxide. You've got the melting and you've got the boiling point of these ionic compounds. Now, ionic compounds have a very high melting point, which means in turn they should have a very, very high boiling point. And we can see that clearly by looking at the data in this table. But the melting point of sodium chloride and magnesium oxide are different. Sodium chloride has a melting point of 801 degrees. And magnesium oxide has a melting point of 1413 degrees. And what you need to be able to explain is why there is this difference in melting point. Why does magnesium oxide have a higher melting point than sodium chloride? If you can work it out, that's good. If you can't, you might want to pause it at this point and to either draw the dot and cross diagram for sodium chloride and magnesium oxide and work it out. We'll start by writing sodium chloride on a piece of paper and magnesium oxide, just a formula, and see if you can find a link between the formulas that you've got. Okay, I'm going to run through it. So if you start by writing sodium chloride on a piece of paper, right next to it the two ions that form sodium chloride, and that's the Na plus ion and the Cl minus ion. Write magnesium oxide on a piece of paper and you'll notice it's formed from Mg2 plus and O2 minus. And the clues there. In the first case, you've got a single positive charge and a single negative charge. In the case of magnesium oxide, you've got a 2 plus charge and a 2 minus charge. There'll be a stronger electrostatic force of attraction between the Mg2 plus and the O2 minus than between the Na plus and the Cl minus, simply because you've now got twice the positive charge and twice the negative charge. It's like two magnets. If you double the two magnets' strength that you've got, they will be attracted to each other a lot more strongly. Okay, so magnesium oxide has a higher melting point because the electrostatic force of attraction between the Mg2 plus and the O2 minus ions is stronger than that between the Na plus and Cl minus ions. Therefore, more energy is required to break the electrostatic force of attraction between the Mg2 plus ion and the O2 minus ion, and therefore magnesium oxide has a higher melting point than sodium chloride. So in this case, it's due to the charge on the ions, and in magnesium oxide, it's 2 plus and 2 minus versus single plus and a single minus charge. And the 2 plus and 2 minus will be attracted to each other much more strongly. This concludes the lesson on ionic bonding. Lesson 2 will cover covalent bonding.